All right, so we will now discuss some applications of the dimension theorem. Now, recall that we have proved the dimension theorem in the last discussion, in the last video more precisely. The statement is for any reducible character of a finite group G, the dimension of the character has to be divisor of the order of the group. Okay, so we will see some interesting applications of this. First application is an easy one. So let P be a prime and G be an order of P square. So we have this formula where Ni's are the dimension of the irreducible, distinct irreducible representations. Now you see that so each Ni due to dimension theorem will be 1 P or P square. Now you see none of the Ni's can be P square because then the left hand side will be much more than RHS, and then if some Ni is P, then the left hand side will be P square plus 1 because the trivial representation is also counted in the left hand side. So left hand side will be at least P square plus 1, which is again a contradiction. So each Ni has to be 1, and since each Ni has to be 1, G has to be abelian. So thus, of course, you can say that we can prove this without using characters. In fact, we have done so earlier, but there's another way of proving the proving the same result using characters, and that just shows the applicability of the dimension theorem due to Frobenius. All right, let's look at the second application. So P be any prime, irrespective of odd or even, and G is a group of order. G is a group of order 2P. Again, we will use the same formula. So Ni's are the dimension of the distinct irreducible characters. So the sum of square is just 2P. Now each Ni is a divisor of 2P, so it can be 1, 2P or 2P. Now you see that none of the Ni's can be P or 2P because then the left hand side will be much higher. So since each of this, so since none of them can be P or 2P, so Ni's will be 1 or 2. Okay, so now you see that number of 1 appearing in this. So as I just said that each Ni can be 1 or 2. Now we just want to know how many of them are 1 and how many of them are 2. So let's look at the number of i's such that Ni is 1. So that means number of one-dimensional characters. In one of the assignments that I have given, there a problem is asked to do that says that every one-dimensional character of G is actually a lift of a one-dimensional character of G modulo G prime, where G prime is the commutator subgroup of G, and vice versa. Thus, number of one-dimensional characters of G is same as the number of one-dimensional characters of G modulo G prime. And since by definition G modulo G prime is abelian, so its number of one-dimensional characters of G modulo G prime has to be same as its order. So therefore, number of one-dimensional characters of G, that is the number of I, so that Ni is 1, is a divisor of a being same as order of G divided by order of G prime, is a divisor of 2P, order of G, which is 2P, and so since it's a divisor of 2P, so it can be the 2P, P, 2 or 1. Okay. Now I just leave you to check that the middle possibilities like P and 1, they cannot happen. Because suppose if one of the, so if this number is 1, so in this sum, there is exactly 1 1 and rest of them are just 4. So then the entire thing will be the left hand side is an integer of the type 4k plus 1, and then it's easy to see that for a prime p, 2p can never be of that form, modulo 4. So similar considerations will hold for the other case. So when these 2's are excluded, we are left with 1 and 2p. So that means either all of them are 1. So since this, again, let me just correct myself. So if these two possibilities are gone, then we are just only left with the possibilities 2 and 2p. Since the possibility 2p, all these are 1. So therefore the group has to be abelian. And otherwise, 2 of them will be 1 and the rest must be 2. And in that case, you can just count that the number of two-dimensional characters has to be p minus 1 by 2, because 4 into p minus 1 by 2 will be 2p minus 2, so that the formula, so that now both the sides match. So thus for a group of 2p, where p is a prime, either we have all one-dimensional characters or they are only two one-dimensional characters, and p minus 1 by 2 two-dimensional number of p two-dimensional characters. All right. Now we will see a significant application of the dimension theorem. As I have already told you that the representations and characters of a group actually provides quite important informations about the structure of the group. So already in one of the assignments we have talked about how to show how to see a group is not simple from the character table. Now we will see another such example. So another such application of this. So this says that no finite simple group has an irreducible representation of over C of dimension 2. Okay, so in other words, that if a group has an irreducible representation of dimension 2, then that group cannot be simple. Okay, so to see this, so we prove by contradiction. So assume that G is a finite simple group which has a two-dimensional irreducible representation. Now since G is simple, so the kernel of this row has to be either trivial or G. So kernel is whole G means the action is trivial, but since V is since the representation is irreducible, that cannot happen. So therefore kernel has to be trivial. Therefore what it shows that this map is injective. So thus G can be regarded as a subgroup of GLV, and then passing through a basis of G, we can without any loss in generality assume that G is a subgroup of GL2C. Okay. Now we use dimension theorem to see that G is, the order of G must be even, because it has a two-dimensional representation. So since the order is even, G has an element of order 2. Let's call it small g. Now, so therefore, since G is an element of order 2, it's a matrix of order 2, so then its eigenvalues will belong to this set minus 1 and 1. We will show that all eigenvalues of G are minus 1. Suppose this has been done, then from that we can immediately conclude that since I mean, again, try to understand what I'm saying, that suppose that we establish the claim that all eigenvalues are minus 1, then from that it will be immediate that G has to be minus of identity, because if all eigenvalues are minus 1, then G has to be minus of identity, and that's a serious problem, because then this subgroup 1G is plus minus identity being normal subgroup of G, because that you can immediately see identity and minus identity both are in the center, we challenge the simplicity of G. So modulo this claim that all eigenvalues of G are -1, the corollary is established. Now let's see how to settle this claim. So we want to show that G has all eigenvalues 1. I'm saying that it's enough to show determinant of G is 1, because determinant of G is just the product of the eigenvalues. If determinant is 1, then both of them have to be the same sign. So either both of them will be 1 or both of them will be -1. Both of them will be 1 means G is identity, which is not allowed because G has order 2. Therefore, if we can show this is you can show determinant of G is 1, then automatically from that it will be okay. It will be clear that G has all eigenvalues -1 and -1. Yeah, G. Okay. So now, in order to show that the determinant is 1, let's just observe that the determinant 1, which is a map from G to C star, is actually a one-dimensional character of the group G, because one-dimensional character and same as from G to C star homomorphism. I mean, something is a one-dimensional character if and only if it is a homomorphism from G to C star. So now recall that any one-dimensional character, in fact, this is what we have used earlier, any one-dimensional character of G modulo G prime, any one-dimensional character of G is actually the lift of a one-dimensional character of G modulo G prime. Okay, again let me recall you, this is what it is what is given in maybe assignment 7. Okay, I'm just using that. Now we will now we have to see what this guy is. Since G is simple and non-abelian, so the commutator subgroup being a normal subgroup of G cannot be just trivial, so it has to be the whole of G. So therefore G modulo G prime is the trivial group, so it can admit only trivial character. And so therefore any lift of the trivial character has to be a trivial character. That shows that determinant map is trivial, that is identically 1 on G. And that's how that's what we are supposed to prove. So thus we see that subgroup cannot have any reducible representation, or group cannot have any reducible representation of degree 2 if it is simple. Okay, so we finish this with another application of the third property of algebraic integers. As I have said, that actually provides us one of the most powerful techniques. So namely, if some rational number is an algebraic integer, then it's an integer. So in order to show something is an integer, if we know that's a rational number, we will just try to prove it's an algebraic integer. So we will show another application of the technique, and also that's it is interesting in its it is significant in its own interest. So basically, the situation is the following: that we know chi g is always a algebraic integer. So now it's very natural to ask, it's very natural to be curious when it is indeed an integer. So now we will see that. So this is what we will prove, that for any finite group G, if G is a group element of order n such that any G to the power I, where I is co-prime to the order of G, is conjugate to G, then chi of G for any character chi will be integers. So this is what we will prove now. The proof is based on a simple lemma. What it says, that suppose omega is the nth root of unity, then if we just raise omega to the power psi, where I is an integer which is less or equal to n and co-prime to n, then sum of such omega I is actually an integer. So first we will settle this lemma. So for omega equal to 1, all the terms are 1, so therefore we have nothing to prove. So we will prove for omega not equal to 1. So we are supposed to show this is an integer. Observe that with that, if we add this term, so this term is just saying that omega power I is where the GCD is greater than 1. then actually the sum happens to be the sum of all omega to the power i's, where I range from 1 up to n. Basically, this sum is broken into two parts. In one part, you have precisely those i's which are coprime to n. On the other part, you have precisely those i's which are not coprime to n. So the sum is equal to this, and since omega is a root of unity, and omega not equal to 1, so therefore this 1 plus omega square up to omega to the power so omega up to omega to the power n minus, I think here it will be yeah. So it is we can see that it's so it is just sum of the power. So omega, this is what is this? This is just omega square plus omega to the power n, and then omega to the power n is just 1. So basically 1 plus omega plus up to omega to the power n minus 1, which is 0 because omega is a root of unity and omega is not equal to 1. So since the sum is 0, so in order to show this is an integer, it suffices to show this is an integer. Okay. So now again we will break this sum into several parts depending upon the GCD of I and n. So for each divisor d of n, we will consider those omega to the power i's, so the GCD of I and n is d, right? And so based on d, we break the sum into several parts, and according to our consideration, d has to be greater than 1. Okay. So thus this sum is sum overall d dividing n and d greater than 1 of these entities. Now, if you have a closed loop, so omega to the power I, so since d is GCD of I and n, so I can be written as as a multiple of d. So therefore, this sum is actually this sum is actually equal to this. As I said, this sum is actually equal to this, because I is allowed to go up to n, being a multiple of d. So therefore, this is what the case. So I is dj, where j is allowed to be from 1 up to n by d, and of course, if GCD of I and n is d, then GCD of j and n by d will be 1. Now, since d is greater than 1, so n by d is less than n. So you see, we are again having the same kind of sum. Again, we are having the same kind of sum with the value of n has been made smaller. Okay. So therefore, by induction, since n by d is smaller than n, by induction we can argue, and by induction by induction we can argue, and thus each of these terms will be integers. So then so is their sum. So it's simple induction argument, somewhat combinatorial, that you have to break the sum into appropriate parts. So in view of this lemma, now let's finish our main proof. So suppose V is a complex representation of G. So, and whose character is chi. So let omega 1 up to omega m are the eigenvalues of rho g, so that chi g is just their sum. Now for any I just want to know what chi g prime I is. So chi g prime I is the sum of the eigenvalues of rho g prime I, and for rho g prime I we have already argued earlier, and in fact this is what we have all used several times in the classes, that rho so if these are the eigenvalues of rho g, then the eigenvalues of any power or eigenvalues of any power of rho g will be just sum of the powers of these eigenvalues. So precisely the eigenvalues of rho g to the power I are this, so that this is this. So now if we just take their sum, the sum will be just sum of the corresponding rows. So for each j from 1 up to n, we have the sum of this kind. Now, from the previous lemma, we know that this is an integer, so therefore the sum over all j. So for each j, as I said, for each j, this guy is an integer, so therefore when we take the sum over j, that also happens to be an integer. Fine. So thus we get this guy is an integer. Then what is this guy? We have already assumed that all gi's such that I is co-prime to 1 is conjugate to g. So therefore, each of this summand on the left hand side is actually same, right? And how many such summands are there? Number of i's which are co-prime to n. So that is given by the Euler's phi function. So this left hand side is phi n times chi g. Okay. So that's what we get. What we get, the phi n times chi g is an integer. Therefore, chi g is an algebraic integer. Right? Now, sorry, phi n times chi g is an integer. So therefore, chi g is a rational number. And already we know that chi g is an algebraic integer. So from there, it follows that it's an integer. So now, again, this is another application of the third property. So again, let me remind you that this actually gives you a very powerful technique of showing something is an integer. Okay. So we have seen two applications of that. The one is, of course, the dimension theorem itself, and the second one is when the values of the characters are always a sufficient condition that ensures the values of the characters are always values of the character is in Z. Okay, so with that we will finish. So now we are on the way of proving the Burnside's theorem, which says any group of order p to the power a and q to the power b is solvable when p and q are primes. So we will do that. That is our next aim. But in order to do that, we need some results from fields. So therefore, first we will review some results from fields which will be necessary, and then using them we will go for the proof of the Burnside's theorem. So this is going to be the content of the next few video lectures. Okay, I will stop here.